Hello Math 3211 students, let's begin Lesson 3, Divisibility Theory 2. This is a continuation from the previous week. In previous week, in Lesson 2, we went through two humongously important theorems. Remember those? Number 1, the division algorithm. Remember this? Such that. And then Bézout's theorem on the greatest common divisor. This one right here. Remember this? Now, do you remember the proofs? Interestingly, the proofs were more or less similar because they are both based upon the same principle. The property that the set of whole numbers W is well-ordered, or the set of positive integers C plus is well-ordered. And then, using those properties, oh, not this one, where is the proof? We begin with a cleverly designed set, which is based upon the target. What do we want? We want A equals to QB plus R, set up the same way. Does it look a little bit differently? No, not really. If I flip over this BX to the other side, then this is the same as, okay, let me write it again. Flip this BX to the other side, we get A equals to BX plus Y. Okay, compare this and that. Are they the same? Flip BX to the other side, and that's what we get here. So this is target, which I just highlighted in blue. That's a target. I didn't highlight it in blue. And then divide your set in the same fashion within W. And then that's well ordered, you can find the minimum. And that minimum is going to be, well, minimum of this Y. So that's going to be a remainder in this case. And then later you have to prove all those properties of that quotient and remainder, and then also the uniqueness. In any case, the starting point was this set with a subset of W, and that's well ordered, so it has the minimum. That was the basic idea, the hardest part, the most creative part of this proof. How about Bézout's theorem? The trivial case of chaos, and then we go through similar concept basically. Divides a subset of Z plus, which is a subset of W, so it's also well ordered. And what we want this, which I just highlighted in red. So we devise a certain subset of Z plus that's based upon the same thing. And then this is a subset of Z plus, which is well ordered. So we can find the minimum here. And that happens to be the greatest common divisor D. Of course, in order to find the minimum exists, the key point is to prove that this is non-empty. And the same goes here. You have to prove that this is non-empty. In that case, you could argue this is non-empty because you could take X as negative as possible, kind of like moving X to negative infinity, kind of like that, as we have been doing in analysis classes many times. And for this case, just find a special example, set X as A and Y as B, then we get A squared plus B squared, which is positive. So remember those. We used the well-ordering principle for both of those humongously important theorems. And then we went through a lot of applications on those. That pretty much concluded Lesson 2. Okay, that was a quick reminder. A very, very brief review. Now let's go to Section 4. The GCD of more than 2 integers. Before that, let's review some properties of the GCD. commutativity, associativity, and distributivity, and so on. And the proofs are left to the students. Not difficult, but can be a bit tedious. Tedious, yes, but let's talk about it briefly. I'm not going to go through with this a lot because it is going to be tedious. So let me copy and paste that thing here. Okay, this is our target. And first, whole number. And second, common divisor. And the third, linear combination. Let's focus upon the linear combination part. The other part, I'm going to completely leave to you. So how do you get commutativity? Well, that's based upon MD is equals to AX plus BY can be rewritten as BY plus AX, so that we have a linear combination of Y and X. So that will lead you to commutativity. Too trivial, isn't it? How about this one? GCD of, so this is GCD of BC and the GCD. So you can rewrite this as GCD of A and GCD of BC, like this. And then likewise, like that. But, oh, it's too cumbersome. So in this case, it makes a lot of sense to use just this A comma B expression, X comma Y expression to make things simplify. It was okay to write GCD here, but this here, too cumbersome. I'd not do this. Yeah, let's just keep it this way. Okay, how does that thing work? Let's see. Let's consider this one first. So let's see. Let's go with, say, D1, and then that's gonna be B X plus CY, like that. That's gonna be this one here. So the GCD that you actually want is A times, okay, I'm running out of character. I cannot use X anymore. AZ plus BX plus CY, and then I need another character. Okay, all right. So eventually all these can be rewritten as A x1 plus B x2 plus C x, where x1 is same as Z, and then x2 is X times W, x3 is Y times W. Yeah, you can rewrite like this. And you can do something similar to this guy. B2, oops, is, okay, A, and then I'm really running out of characters here. R plus B, S, kind of like that. And then putting this to the right hand side here, you can get, oh my, another character, D prime. So that's AR plus BS, and then something still different. Oh my goodness, T plus, and then C RSTU, all right? And then eventually you're gonna get A x1 prime, B x2 prime plus C x3 prime. So either way, you can prove that they're both under this linear combination expression, and then they're both greater than or equal to 0. And then the key thing is, are these two the same? Well, you'll have to use this, the common divisor of A, B, and also C, to prove that D divides D prime and also D prime divides D so that they are the same. Tedious, but you can do it. But being tedious, this thing is rarely worked out by anybody or anybody who writes a textbook or notebook or whatever. I'll do the same. And okay, this one and all those, yeah, I'll leave all those to you. Set all those as linear combinations by step, and then it's not too difficult to show that they're all non-negative. Now, when you show one and the other, they are the same, we'll have to do this. D divides D prime and D prime divides D, so they are the same. The same way we proved the uniqueness of the GCD will apply for the uniqueness or equality in all these cases. The detail is left to the student, and partly based upon those, we can go ahead and define the greatest common divisors of more than two integers recursively like this. You see, it doesn't matter I start from first or the last, because we proved those. Here our textbook authors started from the last, and then in general recursively like this. So it's a recursive definition, so it works out. And whether you put the parenthesis to the left or to the right doesn't really matter because you already showed it. So detail is left to the students. And then we have this. And here, as a matter of fact, I neglected one thing. To tell the truth, D is greater than or equal to 0. That should have been there. It was small things, so I neglected it, to tell the truth, as a matter of fact. That should have been there. So first ingredient, non-negative, greater than or equal to 0. And the second ingredient is this one right here. Common divisor. So it divides everything. A1, A2, A3, A4, and so on, everything, all the way up to the AN. So that's the second ingredient. And the third ingredient is this one here, linear combination. And then each component, did I say component? Excuse me, each coefficient here, those are integers for all indices I. How to prove those? Well, that's left to you. This one is really trivial, so it's not really worth doing anything. As a matter of fact, clear from the definition because it came from the GCD definition of two integers. You see, this is an integer, GCD is so previous. So it's GCD of two integers. It came from that, so this thing is trivial. And then passing these on over to dividing A1 and dividing the GCD, consequently, each of these, or those, by inductive hypothesis or recursion, whatever you may want to call, the detail is left to the students. And then this one, well, we already went through some part of it, as I was showing you this thing here. After putting a lot of characters here and there, yeah, you may run out of characters, but in the end, you end up with this linear combination expression. A bit tedious, but you can do it. As usual, the detail is left to the students. And finally, relative prime. If pairwise relative prime, then arbitrary string is relative prime, but not always the other way around. So for example, if you have GCD of 4, 6, 6, 10, for example, they're all even, so they're not relatively prime. But if you put something like this, now because of that, it's relatively prime. Pairwise, they're not relative prime, but overall they are. We'll have those kind of situations too.